Hello and welcome to this GCSE Physics exam preparation video on waves in air, fluids and solids. And don't forget to like and subscribe. Waves can be either transverse or longitudinal. A longitudinal wave is where the direction of disturbance is parallel to the direction that the energy is travelling. So we have our diagram here with the direction of the energy transfer and the direction of the disturbance. We also have areas of compression where the wave comes together and areas of rarefaction where the wave moves apart again. Examples of this kind of wave are sound waves and P waves, which are a type of wave generated by earthquakes. These waves need particles and so are mechanical waves. The particles themselves do not travel along the wave, they only oscillate, vibrate, around a fixed point. A transverse wave is where the direction of disturbance is perpendicular to the direction that the energy is travelling. So on our diagram, we've got our direction of disturbance, and you can see that that is perpendicular to the direction that the waves are moving in. Examples of transverse waves are ripples in water, all electromagnetic waves, and S waves, which are generated by earthquakes. Some transverse waves are mechanical waves and need particles, for example, water ripples. The particles do not travel along the wave, they only oscillate around a fixed point. Some transverse waves are not mechanical and do not need particles, so can travel in a vacuum, for example, all electromagnetic waves. These are some of the key terms that you need to be able to describe a wave. Amplitude. This is the maximum displacement of a point on a wave from its undisturbed position. Wavelength. The distance from a point on one wave to the equivalent point on the adjacent wave. Its symbol is lambda and it's measured in metres. Frequency, the number of waves that pass a point each second. Its symbol is little f and it's measured in hertz. The period, this is the time taken for one wave to pass a point. This wave shows reduced wavelength and so it increases the frequency. The period of a wave is the time it takes for one complete wave to pass a point. The equation for this is t equals 1 over f. Or period equals 1 over the frequency. The units, period, capital T, units are seconds, lowercase s, frequency, lowercase f, units are the hertz, capital Hz. The speed of a wave can be calculated using the following equation. V equals f lambda, or wave speed equals the frequency multiplied by the wavelength. The units are wave speed, little v, is in metres per second. Frequency, f, its units are the hertz. And wavelength, lambda, its units are metres. You can find the speed of sound in air and the speed of waves in water by following these simple procedures. First, sound is a wave and waves reflect. In the case of sound, we call this an echo. If you stand a known distance measured with a tape measure from a reflective surface, such as a wall, and measure the time taken between the sound being emitted and the echo being heard, and measure this using a stop clock, you can then halve the measured time and substitute the numbers into the equation distance equals speed times time. Rearrange and calculate the speed. For a water wave, you can time how long it takes for one wave to travel the full length of a trough. You measure this time using a stop clock. Measure the length of the trough using a metre ruler. Then again, use the equation distance equals speed times time. Substitute in your numbers and rearrange to work out the speed of your water wave. Both of these experiments are more accurate if they are repeated and means are calculated. Any anomalous readings should be ignored and left out of your mean calculations. And don't forget, you'll also need to revise the required practical for calculating speed in waves and in solids. When waves interact with boundaries between materials, they can be reflected, absorbed, or transmitted. When the wave hits the boundary between two materials, here we have air and glass, some of the wave's energy is reflected. Some of the wave's energy is transmitted through the material and it's refracted on entry, but more on that in a different video. Some of the wave's energy is absorbed by the material and this increases the temperature of that material. You need to be able to draw an accurate diagram for reflection. In reflection, you should have your incident ray, and that should hit the boundary at the point where the normal meets the boundary. And the normal is a construction line which is perpendicular at right angles to the boundary. You will need a protractor in your exams, don't forget it, to be able to draw these accurately. Measure the angle of incidence, again using that protractor, and then draw your reflected ray coming from the boundary at the same angle to the normal as the incident ray. Your labels are as follows. Your incident ray is the ray that hits the mirror. The angle of incidence is the angle between the incident ray and the normal. The reflected ray is the ray that comes off the mirror. The angle of reflection is between the normal and the reflected ray. And whenever you're doing reflection diagrams, you must remember that the angle of incidence equals the angle of reflection. There are two types of reflection that you need to know about. Specular reflection, this is reflection on a smooth surface, and diffuse reflection, which is reflection on a rough surface. In both cases, the incident rays are parallel and the law of reflection is obeyed, but in diffuse reflection, the reflected rays are scattered because the surface is at different angles. Scattered light cannot produce a clear image. Reflection in a plane mirror is an example of specular reflection. Light rays are reflected normally, but the light appears to come from within the mirror. That's why the mirror images appear to be as far behind the mirror as the object is in front of it. These are the virtual rays, and these show where the light appears to come from. Sound waves are longitudinal, and so need particles to propagate. The closer the particles, the better the transmission. Sound travels faster in solids than in air, and the consequence of this is that the wavelength of the sound is lowered as it enters a solid from air. And if we look at the wave speed equation, we can see why. The frequency of the sound will remain the same, but if the wave speed is increased as it moves from air into solid, then the wavelength must lower. Compressions and rarefactions in sound waves cause differences in pressure. These pressure differences are what cause the particles in a solid to vibrate. An example of this is when the sound gets to the eardrum. Sound waves are collected by the pinna and then funneled into the ear canal. The compressions and rarefactions cause the eardrum to vibrate. These vibrations are passed onto the ear bones and then onto the cochlea. Here the vibrations are converted into an electrical signal which is sent to the brain. Humans can hear between 20 and 20,000 Hertz. Anything higher than 20,000 Hertz is considered to be ultrasound. Anything above 20,000 Hertz, higher than humans can hear, is called ultrasound. It's still sound and so reflects, echoes in the same way that sound we can hear does. We use ultrasound to detect things that we can't see, for example, cracks in metal rods, and for medical scans. In this example, the crack reflects the ultrasound back before the ultrasound that hits the end of the block. From this information, the distance of the crack can be calculated. Sound is also used for detecting objects in deep water. This is called echo sounding. Vessels send out sound waves and measure the time taken to receive the echo. The vessel knows the speed of the waves sent out, and by halving the time measured and using the speed equation, the depth of the water can be found. Knowledge of seismic waves and their detection has provided evidence of the structure of the Earth. Earthquakes produce seismic waves, primary waves, P waves, and secondary waves, S waves. P waves are longitudinal waves and can pass through fluids. S waves are transverse and cannot go through fluids. The time delay between the two types of wave being detected and the locations that they are detected at gives information about the inside of the Earth. And that's all for this video. Thank you so much for listening.